Have you ever wondered how scientists can describe literally everything, from a simple falling apple to a crazy fast rocket ship, using the exact same set of rules? Well, today we're going to learn the universal language that makes all of that possible. We're starting from the ground up with the absolute basics of measurement and building our way to the physics of motion. Let's jump in.
So, really, how do we do it? How do you describe a car hitting the accelerator or a ball dropping to the ground in a way that anyone, anywhere on Earth can understand perfectly? The answer is, we had to build a whole new language, a language based on measurement, with strict rules about being precise that gives us the power to tell the story of reality itself.
You know, every language has to start with an alphabet. And in the language of science, our alphabet is a set of standards that everyone has agreed on for measurement. They're called SI units. This is our foundation.
Okay, take a look at this. It might seem simple, but believe it or not, these 7 fundamental units are the only letters we actually need. I'm serious. Every other physical thing we can measure, from the thrust of a jet engine to the energy blasting out of a star, is just some combination of these 7 basic ideas, like length, mass, and time. They are the absolute bedrock of all physics.
So if those 7 units are our letters, what happens when we start putting them together? Well, just like in any language, we start forming words. And in physics, these words are what we call derived units, and they let us describe much more complex ideas.
Let's see how this works in practice. Check out speed right here. Its unit is meters per second. All we did was combine the letter for length, the meter, with the letter for time, the second, and boom, we've created a brand new word that perfectly describes how fast something is moving. It's such an elegant and powerful system.
Okay, so we've got our alphabet and we've got some basic words. But just like any language, you need grammar, right? You need rules. In science, that grammar is all about being precise and, honestly, being honest. It's not enough to just get a number, you have to communicate exactly how much you can actually trust that number. And this brings us to 2 of the most important and, most confused words in all of measurement: accuracy and precision. Accuracy is all about hitting the right target. Precision, on the other hand, is about hitting the same spot over and over again, whether it's the right spot or not. And here's the key takeaway. You can be incredibly precise without being accurate at all.
This target analogy makes the difference just pop. It's crystal clear. Now the goal, obviously, is that top left one, accurate and precise. You're hitting the bullseye every time. But look at the one next to it, precise but not accurate. This is a super common trap in science. It means your tool might be giving you the same result again and again, but some hidden error is making that result totally wrong. You're consistently missing the mark.
So how do we show this precision in the numbers we write down? That's where significant figures come into play. Think of it like this. If your scale at home only measures to the nearest pound, you can't just go and claim you weigh 150.27 pounds. Significant figures are like the grammar rule that forces you to only report the digits you can actually trust. It's about not overstating your case. All right. We've got our alphabet, those are the SI units. We have our grammar, that's accuracy and significant figures. Now we're finally ready to use this new language to tell our very first story, the story of motion, or what physicists like to call kinematics. The story of motion, every single time, starts with one simple question: where is it? In physics, we call this position. It is the starting point. It's the "you are here" dot on the map of the entire universe.
But of course, things rarely stay put. The change from one position to another is what we call displacement. Now, what's really important to get here is that displacement only cares about where you started and where you ended. It doesn't care about the winding, scenic route you might have taken. It's just the net change, from A to B.
So how quickly does that displacement happen? Well, that's velocity. And this is not the same thing as speed. Speed tells you how fast you're going, 60 miles per hour. But velocity tells you how fast you're going and in what direction, 60 miles per hour due north. That direction is absolutely critical. It's basically speed with a compass.
And what happens if your velocity changes? What if you step on the gas, or slam on the brakes, or even just take a turn? Any change in your velocity, and that means changing your speed or your direction, is called acceleration. This is the concept that lets us describe every single change in motion.
A perfect example of acceleration is happening literally all around us, all the time. If you drop something, anything, Earth's gravity makes it accelerate downward at a rate that's almost perfectly constant, 9.8 meters per second every single second. This number, we call it g, it describes the relentless pull of free fall.
So, we've gone and built this entire language of physics,
But why does any of this matter outside of a classroom or a lab? Well, because this is the language used to build, design, and run the world around us every single day. I mean, really think about it. When a doctor gives you medicine, the difference between a milligram and a microgram could be the difference between getting better and, well, a crisis. When engineers design a bridge, they're relying on super precise measurements in meters and a deep understanding of forces using kilograms and seconds to make sure that bridge doesn't collapse. This language has real, life or death consequences.
At the end of the day, this isn't just some niche skill for physicists. Having a solid grasp of how measurement and units work is a truly foundational building block for pretty much every scientific and technical field you can possibly imagine.
So we've done a lot today. We've gone from the 7 basic letters of reality all the way to crafting the rules and the words we need to describe motion. We can now say with precision where something is, how fast it's going, and how its motion is changing. But that leaves us with a giant, nagging question, doesn't it? We know how to describe motion, but we still don't know why it happens. What's the push or the pull that actually causes acceleration to happen in the first place? Well, that's exactly where we're headed next time.